Okay, so on to our experimental procedure for part one here. So this is a pretty simple setup. What we need is two things. We need our iPad, and I've got this opened up to the part one table here. I'll talk about that in a second. And I've got a container that's filled up with 128 pennies. That's going to represent our radioactive material, radioactive uranium-235. And so what you want to do in a second here is pause the video and actually count out to make sure that you do have 128 pennies in here. The experiment's going to be difficult to do if you don't have that exact number. So I'll give you a second to do that. Pause the video, count out 128 pennies. Then what I want you to do is put the pennies back into the jar, close the lid here. And so, again, this is representing radioactive uranium-235. We know that most igneous rocks, rocks that form from magma, will decay from this unstable uranium-235 into stable lead. Now, the half-life is the time that it takes for half that material to decay at any given time. And we know that the half-life of the decay of uranium-235 to lead-207, remember, is 700 million years, or we could say 0.7 billion years. And so what we're going to do is, the thing with radioactive decay is we talk about the time it takes for half the material to decay, but in actuality, it's going to not be as simple as just half and half and half and half. So what we're going to do with this experiment is to model that difference. And so, for example, in this table, I actually already have the right-hand column filled out, and you are going to want to copy this down, actually. This is going to be what our expected half-life would be after each successive round of decay. And so, for example, round one is representing the first half-life, and so we start with 128 pennies. We would expect, so this column right here is the expected number of heads. This will be the actual number of heads. The heads are going to represent radioactive uranium. And so the expected number of heads after one half-life, we would go from 128 to 64. We would expect after the first one, just like we did in the last example, we'd expect to go from 128 down to 64 uranium. That would also mean that we have 64 lead, right? Because it's always going to add up to 128. And we'll talk about that later as we do this. And so we go from 128 to 64. Half-life 2, you'd expect 32 uranium. Again, this is the parent isotopes. Half-life 3, you'd expect 16. Then 8, then 4, then 2, then 1, then 0. If it comes to it in our experiment, we might need to add more zeros, but we'll wait for that. So you want to copy this data down. This is our expected data, the expected decay after each half-life. We would expect to get 64, 32, 16, 8, 4, 2, 1, and then 0. Now what we're going to do for this experiment is we're going to take our 128 radioactive uranium-235s, and we're going to model what this decay curve will actually look like in real life. And so it's a pretty simple procedure. What we want to do is we want to take up the pennies, and then I'm going to uncap the jar here, and you want to dump them out. And so what we're going to do is you're going to start to separate the heads and the tails. The heads are representing radioactive uranium, and the tails are representing now the new stable lead. Remember, the radioactive uranium is going to keep decaying, and the stable lead is going to stay as part of the rock forever. So what you want to do is you want to separate out the heads and the tails, and we're only going to count the heads. So we only want to count the heads. You can ignore the tails. That's our stable material, and you know that the tails is going to add up to, when you count the heads, the tails will have to, in addition to the heads, add up to 128. So let's separate heads and tails right now. Okay, so I separated my heads and my tails for this experiment. So what my data turned out to be was 76 heads, which represents the unstable uranium, and 52 tails, which represents stable lead. So again, though, remember, this is the parent isotope that we're looking at. So this is the uranium, the heads that we're looking at. And so for this number right here, we're going to put 76. So this is kind of a thing that confuses people. So these don't have to add up to 128 because these are both uranium. These are both our uranium. This is our actual versus our expected. So we would expect if we, with one half-life, we would get 128 and we'd go down to 64. In reality, though, we actually got 76. And so you're going to count and put in whatever you get for your heads. The tails, I just counted that out so that you could see that, but we're actually going to just push these off to the side. You're not actually going to need that, right? Now know, though, that this is always going to stay part of the rock. So the rock will always have at least 52 lead, and the 76 uranium, we're going to perform another half-life, and we're going to see how much that decays. And so basically, think about this. The unstable uranium is always going to get smaller. The stable stuff, the lead, is always going to get bigger. And so what we want to do then is we want to collect all of these heads and into our container. I'll do that right now. So now in here I've just got my 76 heads that's representing uranium, and this is going to keep decaying. So what we're going to do is we're going to perform another experiment. I'll shake this up, and I'll dump them out again. And you want to do the same thing. We're going to separate out the heads and the tails, because this is our half-life 2 now. We've gone through 2 decay curves. Okay, so part 2 then, I had counted these out already, and I got 38 heads. So I'm going to write that into here. And so just make a note then, I went from 76 to 38. Now these are pretty close, but they're not what you would expect to get in a true 50-50% probability half-life. And so what we're going to do is we're going to keep comparing this decay curve to see how precise our real data is to what we would expect. So again, I'm going to collect the heads. We're going to put them into the container. We'll shake it up, and you're going to dump it out. And the goal is to keep doing that for round 3, 4, 5 until you run out of heads. So you're just going to keep doing this. You'll separate out the tails, you'll count the heads, and you'll keep doing that until there are no more remaining heads. So I'm going to skip a few steps. I'm going to perform this experiment a few times, and then I'll show you what my data looks like at the end. You're going to want to perform this experiment as well. So I'd probably pause the video at this point, perform this experiment again, take your jar, flip it, separate out the tails, count the heads, and then you write the heads down in this left column here. Again, this can already be filled out, so you can already write 64, 32, 16. This is what you would expect to get, and this is what you actually get. So perform the experiment a few more times until you run out of heads. If you have to go past round 9, just create a round 10 below here, and you'll write in your data below, and you'll keep carrying over the 0, because you would expect by round 8 you should be done, but that might not be the case. You might get 1, 1, 1, 1. You got to keep doing it until you run out, basically. We'll see how far you can take that as we go. All right, so this is it. I had to go to trial 10 here, so I had to fill in just one row down here below, and so I got kind of stuck on 3 here, and then I ended up with 0 heads on round 10. Now I've seen people have to go past round 10. I've also seen people finish before round 10. Your data, if you're doing this in class, should not look the same as mine. It would be extraordinarily unlikely that it would be the same as mine. And so unless you're doing this outside of class, distance learning, this data should look completely different. And then what we're going to do on the next step is we're going to plot this in graphical analysis, and then we're going to, so that we can compare what our actual number of uranium, our actual number of heads looked like versus what we would expect. So again, your column should definitely look like this, except maybe you don't have as many zeros, or maybe you have more zeros, but your column for this one should be the same as mine. This should probably be different if you're doing it in class. And so then we're going to graph it, and then we'll analyze. Okay, so now it's time to plot our data on graphical analysis. So I've got graphical analysis pulled up. My suggestion, so that you can do this pretty easy, is I've already split screened the Ages of Rocks lab data. And so we're going to plot this on our graph so that we can see what this looks like side by side, basically. So I'm going to click on New Experiment and go to Manual Entry this time. You're going to get a blank table that looks like this. Now the problem with this is right away is that you have 2 sets of data right here. I see an X and a Y, but we actually need to create 3 columns. So we've got column 1, which is our half-life. We've got column 2, which is our actual. And we've got column 3, which is our expected. And so what we need to do is we just need to create a 3rd column. So I'm going to click right here on this triple set of dots. I'm going to go to Add a Manual Column. Now, the one thing you need to know, and this is going to be true for all of the graphs that we make in classes, when you hit Add Manual Column, it's going to be your rightmost column that you're creating. And so we're going to actually create this expected right here. Expected uranium. And the units for this one are just going to be pennies, because that was our number of pennies. So you would expect, we would expect 128, then 64, then 32, and we'll talk about that in a second. I'm going to have to pull out of this really quick. I'm just going to fully split screen this right here. And so I'll click done on that. So you've got your expected uranium. Now for these last two columns, we're going to click, instead of add manual column, you're going to click on column options. And you just got to rename these. And so this one was our middle one. So this is going to be actual uranium. Again, the units are pennies. And so we've got our actual, our expected, and then this other one right here. So I know that this one is unlabeled. We're going to label it just to make it clear here. So I'm going to go to column options again, and I'm going to type in number of half-lives, or just so this is half-life. So round 1 is half-life 1, round 2 is half-life 2, and such. And we can actually just call the units. We can also call the units half-life 2, half-life. And so what we're going to do is you've got your 3 columns. Now we're just going to fill this out, basically. So I'll let you fill out yours. We'll start out going 0. I've got 70. Oh, sorry. We're going to start with 128. So at half-life 0, we were at 128. So that's before our trial. We need to have that 0 number here, 128. And then to create another row, you'll just hit next on your far right column. And that creates a second row. So I'm going to move this back so that we can see this. And so what you're going to do is you're going to follow through. We'll go 1, half-life 1, and I had 76 for my actual, and I had 64 for my expected. So you're going to continue down, and you're going to fill in this graph just like I have here. And so we'll come back and we'll look at how to process this data at the end. All made right here. And so this is complete. I went down to trial 10 for me, which was the time where I hit double zeros. Make sure that you have a half-life 0 with 128 and 128 up here. Let me know if you have any questions while you're having, if you're having a hard time getting this filled out. And so then the only remaining steps we have to do to make this data look really nice is right now I've only got one. I've got my actual data showing up, which is the middle column. What I need to do is make sure that on the y-axis I click right here and I click on my expected. So you should have 2 lines. And then what I want to do, and I have half-life down here on the x-axis. Then what I want to do is click on the bottom left right here. I'm going to apply a curve fit. Now, this is not the proper curve fit. This obviously isn't a linear decay. This is actually, well, do you know what kind of decay this is? It's actually exponential decay. And so what we want to do is we want to go down to natural exponent right here. And so that's going to be the curve fit that we apply. Now, what I would do like this is where I would screenshot my data so that you have this information. We're gonna use some of this as we go beyond in this lab. So I'll screenshot my data right now. And that's what we'll put into our lab sheet right here in this part. And then we just have one more thing that we have to do. We're going to go down to, so you're going to answer these questions. Those will be related to your graph. This last part here, this table, this is going to be something that you're going to fill out on your own. I'm going to walk you through how to do the first, let's say 2 of these, just so that you have a good idea of what to do. And so the important thing is now we're going to actually show how we use this data to find how old a specific rock sample is. It's going to be really important to read through these sets of bullet points here, just because that's going to give you all the information that you need. For example, right here, it tells you that you're going to use 0.7 billion years for every half-life that elapses. So a couple things that you can fill out right away is we're going to go through our half-lives along the row right here. So for number of half-lives, we could actually just fill that out. This is going to be 1, 2, 3, 4, and 5. That's pretty easy. That's definitely the easiest step. And for this part of the experiment, it's going to be really important that you make sure you read this, that we're going to use our expected results. So again, what you're going to do with this table is you're going to analyze the difference between the actual and the expected number of heads that we got. for the purpose of the table, everybody is going to have the same starting point. We're going to go from 128 to 64 to 32. It's what we expect. That's for the purpose of this part. So we're going to put in 64, and we could actually fill this all the way out, 32. So your data should be the same as mine for this because this is the expected. It was the same for everybody. This part is not your actual data. So 64, 32, 16, 8, and 4, we can already fill that out. That's pretty easy. Remember that we started with 128 uranium. And so we started with 128 uranium. The key here is, let me use a different color. The key is when I have the decay from 128 to 64, what I've done is I've created 64 uranium and 64 lead. So I've got 64 uranium, but I've also at the same time created 64 lead. This is where it gets a little bit tricky, but it's really important to follow along here. This lead is locked in the rock forever. So at every point from now on, we're going to have at least 64 uranium and at least 64 lead. It's got to add up to 128 at every step. So that'll be true for half-life 2 as well. They're always going to add up to 128. The key is that the 64 lead stays the same. The 64 uranium is going to constantly get smaller. As you see right here, it decays every single step. And at each half-life, it's the amount of time that it takes for half this material to decay. This is what we're going to use to be able to age the rocks. In the case of this ratio right here, these will be pretty easy at the beginning here. This is 64 to 64. And if you simplify that ratio, that just equals 1 to 1. That's your answer. I would kind of box that in right there just so you can show that that's your answer, because there's going to be a little bit of math you have to do for the following ones. We know that this was at half-life 1, and we said that every half-life, it takes 0.7 billion years. So this one is really easy. 0.7 billion. It takes 0.7 billion years to complete the first half-life. So I'm going to walk you through one more column, and then I'm going to have you fill out the rest on your own here. So this is the process here. Let me clean some of this up here just so you can see a little bit more clearly. So remember that the 64 uranium will decay down into 32 lead. So how many pieces of, or sorry, the 64 uranium is going to decay down into 32 uranium. How many pieces of lead are we going to have after half-life 2? So the answer for that is going to be, remember that we started with 128. We're not going to create or destroy any of these. And so it always has to add up to 128. So in step 2, we have 32 uranium. So to figure out how much lead we have, you have to go 64 plus 32. We've created a new 32 lead from this split, but we still have the 64 from the previous part. And so you have to always, this number will always be getting bigger as the uranium gets smaller. So 64 plus 32 is 96. Now our ratio, we have 32 uranium, 96 lead. And so what we're going to do is 32 to 96. So to find the ratio, you just have to figure out how many times does the small number go into the big number. And if you did the math yourself, you should get 1 to 3. So your ratio for this one would be 1 to 3 because you have 32 pieces of uranium, 96 pieces of lead. That's after half-life 2. And so what we have to do is, there's a couple different ways you could do this. I would just recommend adding these though. And so we know that every half-life is 0.7 billion years. So we were already at 0.7, and you just add an additional 0.7 billion years each time. So every time you go across here, you're going to be adding a 0.7 to the previous column, basically. So in this case, we have 1.4 billion. And that would be your answer for this bottom one right here. Sorry, that cut a little bit into the other one. And so I'm going to see if you can figure out these last 3 columns, if you can kind of follow the same procedure, and see if you can get the answers for this. This is what we're going to use to find out the exact ages of rocks. But just know that, you know, if we go back to our data table, it isn't quite the case that you're always going to have exactly the same, you know, expected and actual numbers of pieces of uranium that decay. So in reality, there is going to be a little bit of error that's introduced as we go across the table. In reality, it's not always going to be nice, clean decay like this, and so that means that when we get an age of a rock, there's always going to be some kind of range. In class, when we look at ages of rocks, you're always going to see something like, maybe we have a rock that's 2.2 plus or minus, 0.3 billion years old. That's a kind of a wide range of uncertainty, but that's kind of the example of an age of a rock that you would see in reality based off of this experiment here. So I'll see if you can finish this, and that will be it for part 1 of the lab procedure.